This is Daniel Coosbury, and in this video we are going to introduce one of the two major statistical practices for estimating parameters. So in this video in particular, we're looking at how to construct what's called a confidence interval for the population mean, assuming that we know what the population's standard deviation is. And I'll kind of explain what that sentence means as we work through this video. A primary goal of statistics is to estimate unknown parameters from a population. So here's my little box that represents a population, and imagine a situation where we want to know the mean of something, but we don't actually have all the information from the population. And so what we're going to do is we're going to take a sample from that population, take a nice random sample, and from that sample I can learn things like what's the sample mean, what's the sample standard deviation, and things like that. Now we're at a point now where we can use this information to estimate what the population mean is. So kind of one unfortunate fact is, unless you know everything about everybody in any population, you're never really going to know what mu is. You almost never know what mu is, and unless you ask every single person in the population, you're never going to have this information. So what statistics does is statistics uses stuff from a random sample to estimate for mu, and so that's kind of the goal here. Now we're in a situation where we don't know what mu is, but we do know what sigma is, which is a little bit of a strange situation. But imagine a situation where we don't know the population mean, we do know the population standard deviation. There's a few instances where this might be true, and so we're gonna know this, and we're gonna have to estimate this using what's called a confidence interval. A confidence interval is one thing that's used to estimate the mean mu, and the confidence interval has two primary parts. And so this slide's kind of showing you what I mean by confidence interval. The first part of a confidence interval is called a point estimate, which is a single number that provides the best estimate of mu. So in other words, if we don't know what the population mean is, we can take a sample, random sample, and we can come up with the best estimate for mu, which turns out to be X bar. And so imagine this situation where we don't know what this is. We take a sample, and we can actually find this thing. We can find X bar from a sample. And if we had to pick a single number to represent a single number to represent like our best guess at what mu is, it would be X bar right here. However, in statistics, we're not comfortable using single numbers because you can't really say with 100% certainty, or really any certainty, that this is exactly that, or because it could be way off. And point is, we don't like to use a single number. We like to use what's called a confidence interval. But if I was asked for a singular best estimate for what mu is, I would use X bar. So that's what we mean by point estimate. It's the best estimate of mu. In this case, the best estimate of mu is the mean of our random sample. Now, like I said, we don't want to just use this, which is why the confidence interval has another part, the margin of error, which is another numerical value that's both added and subtracted from the point estimate to form the confidence interval. The margin of error is denoted by capital E, and I'll show you how to find what E is in a little while. So what I mean is, we don't want to just use the point estimate. We want to use the point estimate plus or minus a margin of error, and that gives us an interval, not just a number. So I'll say it again. Statisticians don't like just throwing out one number and saying, that's it. We would rather come up with what's called an interval, which is a range of numbers, and say, well, we're pretty confident that the true mean is between this number and that number. So these are two ways to denote an interval. Your point estimate's in the middle, and you add and subtract E. So that's one way to represent a confidence interval. You could say it's this number plus or minus the margin of error. You might see that in polls, for instance. Another way to say it is this is the point estimate minus the margin of error. This is the point estimate plus the margin of error. So sometimes this is called the left endpoint and the right endpoint, or the lower bound and the upper bound. Notice if you subtract the same number and add the same number, then X bar is in the middle of the confidence interval. So let's just say X bar was 2 and the margin of error was 4. well then this would be 2 plus 4, this would be 2 minus 4, and your confidence interval would be -2 all the way up to 6, where 2 is perfect, X bar is perfectly in the middle of this interval, if you want to think of it that way. But anyway, confidence intervals are in two parts, the point estimate and the margin of error. So the point estimate, when you're looking for confidence intervals for mu, point estimate's really easy to find. It's just X bar. The margin of error is going to be more complicated, and we'll work our way up to that by the end of this video. Okay, there's some other ideas involved when we're talking about confidence intervals. Let me kind of read this sentence. Rather than using the single point estimate, the goal of the confidence interval is to provide an interval for which we are reasonably confident that mu lies within it. In other words, rather than saying, it's X bar, rather than saying it's just that, we'd say, okay, well, I'll give you this interval X bar minus E all the way up to X bar plus E, and say I'm reasonably confident that mu is in that interval somewhere. Now, what do we mean by reasonably confident? I just kind of made these words up. Well, what we mean is I'm confident to a certain point, which is dependent on what's called my significance and confidence level. So these are two terms that are important when you're doing a confidence interval. The significance level, which is denoted by alpha, so that's the significance level, is the probability that our interval does not contain mu. So I'm taking a sample, I'm making an interval from the sample, and there's a certain probability that I'm wrong when I make my interval. So the significance level is that probability that I make an interval and it doesn't capture mu. So you can kind of think of this as the probability that you're wrong once you make your interval. That's kind of how I like to think about the significance level. In other words, I'd make an interval and I go through all the work and it turns out mu's not actually in there. This is the chance that mu's not actually in there. The chance that I put my interval in the wrong spot. The confidence level, which is 1 minus alpha, is the probability that our interval captures mu. So notice that if this is a probability, 1 minus alpha is the opposite of that probability. So the confidence level and the significance level are opposites of each other. These are opposites. Meaning that, for instance, if my significance level is A equals 0.04, then my confidence level is the opposite of that, which is 0.96. This would end up, we could call this 96% confidence. So the math here is not complicated, but as far as getting these two terms straight, the significance level is the chance that you make an interval and it doesn't capture mu. The confidence level is the chance you make an interval and it does capture mu. So they're complements of each other. The probabilities are opposite. So if alpha is 0.04, the 1 minus alpha is 0.96, which equates to 96% confidence. I'll show you how to interpret this in a later slide. So keep these two things straight. They're both probabilities. Alpha is the small one. 1 minus alpha is the big one. But they're still both probabilities. In summary, given a significance level alpha, our goal is to be able to construct an interval and say a sentence a lot like this one right here. We are 100 times 1 minus alpha % confident that a population mean mu is between this number and this number. So this is kind of my general shell for how I interpret confidence intervals. Of course, if you tell me what alpha is, then this ends up becoming like a number. For instance, this number, this could be like 99%, or it could be 80%. Once you tell me what alpha is, I can actually write this as a number, some kind of percent. Once you find the X bar and the margin of error, then you have a left endpoint and a right endpoint, and you can say that I'm 99% confident that the population mean mu is between this and that. So like this is just kind of a general shell. Our goal is to be able to say, I'm to a certain level, I'm confident that the mean is in my confidence interval. Let's look at this example. We're interested in how many gallons of milk a family in the U.S. purchased each year on average. We take a random sample for which the average number of gallons purchased is X bar equal to 45.3 gallons. For a significance level of alpha equals 0.05, we compute a margin of error of 4.7. So ignore the fact that I just wrote this down. I haven't showed you how to find that yet. But let's just say that we take a sample and That's our sample mean, and this is the margin of error that corresponds to a significance level of 0.05. So those are the three pieces of information. If I had those three things, then I can say something like this, which corresponds to this sentence up here that I kind of read earlier. So if this is true, then I can say, then we can be 95% confident. So this corresponds to that. The significance level is the opposite of the confidence level. We can be 95% confident that the mean number of gallons of milk purchased by a U.S. family each year is between 40.6 and 60 gallons. So that's how I would interpret my data and that I found. In other words, what I'm saying is the lower bound of this is 45.3 minus the margin of error, which ends up being that. And the upper bound is 45.3 plus the margin of error, which would be 60 even. So I would interpret my findings as this. We're 95% confident that the mean number of gallons of milk purchased by a U.S. family each year is between 40.6 and 60 gallons. So I'm not saying that the mean is this, the population means this. I'm saying the mean is between these two numbers, which is a pretty nice thing to be able to say. Like I've created some kind of interval, and I'm trying to target the mean, and it's between roughly 40 and 60 gallons, which is a helpful piece of information. Of course, there's a 5% chance I'm wrong because I'm only 95% confident. There's a 5% chance I'm wrong and that my interval is wrong. So keep that in mind as well. But this is the goal we're working towards. So now it's probably time to start telling you how we get this margin of error to begin with. So in the previous example, our significance level was 0.05, which allowed us to make an interval for which we're 95% confident that mu lied within it. Of course, we might want to only be 90% certain where alpha would equal 0.1. In other words, like, why did I say alpha is 0.05 earlier? Why couldn't I say alpha is 0.1? Well, it depends on what I decided when I made the interval. So maybe instead of wanting to be 95% sure, I want to be 90% sure. You can do that. You can change it around depending on who's asking or what you want to report. Adjusting the significance level will adjust the size of our margin of error. And that's because the margin of error depends on the significance level. So I'll finally give you how to find the margin of error for this kind of confidence interval. The margin of error is computed by taking z sub alpha over 2 times sigma, which you know, over the square root of n, which is your sample size. So this is known, and this is your sample size. And this is called a critical value. Z sub alpha over 2 is called a critical value. It corresponds to the standard normal curve, standard normal distribution, which you should have worked with before you've gotten to this video. So this is called a critical value, which is an important thing. So this is critical value notation. If you see the notation Z with a little alpha down here, alpha is a significance level. So like, for instance, alpha could be 0.1 or alpha could be 0.05, or it could be, it's a small probability. This refers to the Z-score with an area of alpha to its right. In other words, if I were looking at a standard normal curve, if Z sub alpha means that this area to the right of Z is equal to alpha. Similarly, Z sub alpha over 2 refers to the Z-score with alpha over 2 to its right. So here's a better picture. Z sub alpha over 2 is right here. The area to the right is alpha over 2. So that's what that notation means. It's kind of like the opposite of the percentile notation, where if you remember, we called like P60 was the number for which 60% was to the left. It's kind of like the opposite of that. So it's not this thing, rather the alpha over 2 is to the right, not the left. What this does when you do alpha over 2, you take your significance level divided by 2, is it gives you alpha over 2 over here. It also gives you alpha over 2 over here, and it lets the area in the middle be 1 minus alpha. So all three of these things add up to be 1. The area in the middle ends up being your confidence level, which is why we're doing it this way. So the math works out. If you do alpha over 2, the math works out so that the middle part of your normal distribution is your confidence level, which is really helpful here. So let's look at how to find a critical value and maybe get a little more used to this notation. I want to find z sub alpha over 2 for a 92% confidence interval. Okay, so 92% confidence interval, that means 1 minus alpha is equal to 0.92. So those are the same thing. So that means alpha has to be equal to the opposite of that, which is 0.08. Okay, do you see how this is my confidence level? Is right here. My significance level is this one, right, is the opposite of that. So they're always opposites. Once you know one, you can find the other. And I got the confidence level from this. So now I know alpha's 0.08, which means that alpha over 2 is equal to 0.04. So just divide this by 2. And then I can use my z table to find the value for which the area above it is 0.04. So if I'm looking at on my normal curve, z.04 is down here. The area above it is 0.04, which means the area to the left is going to be 0.96. Okay, so if that's 0.04, that's 0.96. And this is the number I'll use, the standard normal table, to find my z value. Okay, it's a little complicated, I know, but this is the method that we have to use to find these critical values. So I saw my confidence level, I got my significance level, I divided it by 2, which means the area above that value is 0.04. The area below the value, the area to the left, is 0.96. And I need the area to the left in order to use my table or my calculator. So the area to the left is 0.96. You can see on the table at 1.75, you're really, really close to 0.96. So you'll take 1.75 as your value. If you use the calculator, do inverse norm, where this is the area to the left, and then you have the mean and the standard deviation of 0 and 1, respectively. So this is my area to the left, that's the mean, that's the standard deviation. You also get 1.75 if you round it to 2 decimals. So yeah, it's a little, it feels backwards, and it's going to take some practice to get comfortable with, but this is the method. Let me try to highlight kind of how I did these things. So I started here, I got there. Need to draw the arrow better. I got there, and then I went from there to there, and then I went from there to alpha over 2, and then I went to my picture where 0.4 is there, and then 0.96 is on the left, and you need the area of the left to do this. Yeah, it's fairly complicated. Sorry about that. That's the way it works. So that's how you find critical values. And so with the critical values, now we can construct a confidence interval for the mean. And I'll put all this together now. This whole slide kind of tells you how to find a confidence level for the mean with sigma known. And in another video, I'll give you some examples, but I've about run out of time with this one. So if the central limit conditions are met, which are we either have a normally distributed population, or we have n is greater than 30, or both, then a 100 times 1 minus alpha confidence interval for mu, when sigma is known, is given by x bar plus or minus z sub alpha over 2 times sigma over n. So this is my margin of error right here, and this is my x bar. So you could read that as x bar plus or minus the margin of error. Okay, so I just showed you how to find this. This is going to be given to you. If sigma is known, then this is given. When you take a sample, you know what this is. Messed up. You know what this is. And you take a sample, you can find this. If I take a sample, I can find my sample mean. This is given to me. This is from the sample. So really the hard thing in finding and constructing confidence interval is going to be finding the critical value, z sub alpha over 2. And you do it like I showed you on the last slide. This is another way to write the confidence interval. X bar minus the margin of error, X bar plus the margin of error. So it's pretty nice. And on another video, I'll show you how to, I'll show you a few examples of how to make confidence intervals using this method.